Welcome to Cambridge IGCSE Physics, Lesson 61.1, The Sun as a Star. Today we explore our nearest star, the Sun, examining its classification as a medium-sized star, its composition of hydrogen and helium, and the electromagnetic radiation it emits across infrared, visible, and ultraviolet wavelengths. This lesson provides fundamental knowledge about stellar physics and energy radiation that forms the basis for understanding our solar system and the universe beyond. Let's examine our learning objectives for today's lesson. By the end of this session, you will achieve three key outcomes. First, you will know that the Sun is classified as a medium-sized star, understanding its position in the stellar classification system compared to other stars in our galaxy. Second, you will know that the Sun consists mostly of hydrogen and helium, the two lightest elements that fuel nuclear fusion reactions in its core. Third, you will know that the Sun radiates most of its energy as infrared, visible, and ultraviolet electromagnetic radiation, understanding the electromagnetic spectrum and energy distribution. Now let's define our key vocabulary terms precisely. Each term is essential for understanding stellar physics. First, the Sun, which is our nearest star located approximately 150 million kilometers from Earth. It functions as a massive nuclear fusion reactor converting hydrogen into helium. Second, medium star refers to the Sun's classification in the stellar size system, neither a giant nor dwarf star. Third, hydrogen is the lightest chemical element consisting of one proton and one electron, comprising about 73% of the Sun's mass. Fourth, helium is the second lightest element with two protons and typically two neutrons, making up about 25% of the Sun's composition. Understanding these terms precisely is crucial for stellar physics. Let's explore our first core concept, the Sun as a medium star. Stellar classification organizes stars by their size, mass, and luminosity into categories. The fundamental principle states that stars are classified from smallest to largest as red dwarfs, medium stars like our Sun, red giants, and blue giants. The definition of a medium star is one having a mass between 0.5 and 8 solar masses, where one solar mass equals the Sun's mass. Our Sun's properties include a mass of 2.0 times 10 to the power 30 kilograms, a diameter of 1.4 times 10 to the power 9 meters, and a surface temperature of 5,800 Kelvin. The diagram illustrates the size comparison, showing how the Sun fits between smaller red dwarf stars and larger giant stars in the stellar classification system. Now we examine the Sun's composition and nuclear processes. The nuclear fusion process occurs in the Sun's core, where hydrogen nuclei combine under extreme pressure and temperature to form helium nuclei, releasing enormous amounts of energy. The Sun's composition by mass consists of 73% hydrogen, the fuel for nuclear fusion reactions. Helium comprises 25% of the mass, much of it produced by fusion of hydrogen nuclei. Heavier elements make up only 2% of the solar mass. The core temperature reaches 15 million Kelvin, which is hot enough to overcome the electrical repulsion between hydrogen nuclei and enable fusion reactions. The pie chart shows this composition visually, with hydrogen dominating the Sun's mass and providing the raw material for the fusion reactions that power our star. Let's examine the Sun's electromagnetic radiation output. The energy distribution shows that the Sun emits energy across the entire electromagnetic spectrum, but most energy falls within three main regions. The primary radiation types are infrared, visible light, and ultraviolet. Infrared radiation carries 49% of the Sun's total energy output, with wavelengths longer than 700 nanometers. We cannot see infrared light, but we feel it as heat. Visible light comprises 43% of the total energy, spanning wavelengths from 400 to 700 nanometers. This is the light our eyes detect, enabling photosynthesis and vision. Ultraviolet radiation accounts for 7% of the energy, with wavelengths shorter than 400 nanometers. UV radiation causes sunburn and skin damage. The Sun's peak wavelength is 500 nanometers, corresponding to green light, as predicted by Wien's displacement law relating temperature to peak emission wavelength. Let's work through our first example, calculating solar energy components. The problem asks us to calculate the infrared energy received per square meter at Earth's distance from the Sun. We are given that the solar constant equals 1360 watts per square meter, representing total solar energy received, and that infrared radiation comprises 49% of this total energy. Step 1. Identify the total solar energy. The solar constant of 1360 watts per square meter represents all electromagnetic radiation received from the sun. Step 2. Calculate the infrared percentage. We need 49% of the total energy. Step 3. Apply the percentage calculation. Infrared power equals 1360 watts per square meter multiplied by 0.49, which equals 666 watts per square meter. Step 4. State the final answer. The infrared energy received is 666 watts per square meter. The diagram shows the energy distribution with infrared comprising the largest single component. Example 2 applies wave physics to solar radiation. The problem asks us to calculate the frequency of the sun's peak wavelength emission. We are given that the peak wavelength lambda equals 500 nanometers and the speed of light c equals 3.0 times 10 to the power 8 meters per second. Step 1. Write the wave equation. We use c equals f lambda, where c is the speed of light, f is frequency, and lambda is wavelength. Step 2. Rearrange for frequency. Dividing both sides by lambda gives f equals c divided by lambda. Step 3. Convert units. 500 nanometers equals 500 times 10 to the power minus 9 meters. Step 4. Substitute values. F equals 3.0 times 10 to the power 8 meters per second divided by 500 times 10 to the power minus 9 meters. Step 5. Calculate. This gives F equals 6.0 times 10 to the power 14 hertz. The answer is that the sun's peak frequency is 6.0 times 10 to the power 14 hertz, corresponding to green light in the visible spectrum. Now practice what you've learned with these 3 questions targeting different skill levels. Question 1 is basic level, testing recall of fundamental facts. It asks, state the 2 main elements in the sun's composition. This tests your knowledge of solar composition percentages we discussed. Question 2 is intermediate level, requiring calculation skills. It states, calculate the visible light energy received per square meter if the solar constant is 1360 watts per square meter. Remember that visible light comprises 43% of total solar energy. Question 3 is advanced level, testing analytical understanding. The question asks, explain why the sun is classified as a medium star. This requires you to discuss mass, size, and temperature compared to other stellar types. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles about stellar radiation power our modern world. Let's see how today's concepts apply in practice. In solar technology, solar panels convert visible and infrared radiation from the sun into electrical energy using photovoltaic cells. Understanding the sun's energy distribution helps engineers design more efficient panels that capture different wavelengths. In astronomy, stellar classification helps scientists identify potentially habitable exoplanet systems by determining if host stars provide suitable energy output for liquid water. In climate science, solar radiation drives Earth's weather patterns, ocean currents, and seasonal changes through differential heating of the atmosphere and surface. These applications show why stellar physics matters. Career-wise, this knowledge leads to many professions. Astrophysicists study stellar evolution and exoplanets. Renewable energy engineers develop solar technologies. Climate researchers model atmospheric systems, and space mission planners design instruments for solar observation. The concepts you learn today become tomorrow's technological breakthroughs. Let's review the solutions to build your confidence. For question 1, the answer is hydrogen at 73% and helium at 25% of the sun's mass. These are the 2 dominant elements formed during Big Bang nucleosynthesis and stellar fusion processes. For question 2, we calculate visible light energy as 1360 watts per square meter multiplied by 0.43, which equals 585 watts per square meter. This represents the solar energy our eyes can detect and plants use for photosynthesis. For question 3, the Sun is classified as medium because its mass falls between 0.5 and 8 solar masses, its surface temperature is 5,800 Kelvin, and its diameter is 1.4 times 10 to the power 9 meters, placing it between dwarf and giant stars. Now, exam success tips. First, always show your working step by step. Even if the final answer is incorrect, you earn marks for correct method and approach. Second, include units in every calculation step to avoid losing marks. Third, check if your answer is reasonable by comparing to known values. Fourth, read questions carefully, identifying command words that tell you what to do,